Okay, everybody, let's work through a quick practical. So the scenario is I've got a level device, a differential pressure device for a level application. We want to take that differential pressure device that we pull from our stock room, and we're going to take this out into the field and replace an existing pressure transmitter that's in there. But the pressure transmitter, we don't know what was configured in there. So we went out and took some tank measurements. We're going to configure the differential pressure transmitter on the bench before we take it out into the field. So what I've got sitting out on my workbench here is I've got a differential pressure transmitter. Hopefully you can kind of see this as I come around this way. As I got the high port side here, and this actually has both indications on it. It's got an HP and an LP with a plus and a minus underneath it. Okay, so high side, low side of my transmitter on my pressure cell, and then this is a diaphragm on this side, diaphragm on this side, and we're sandwiching or we're wedging that together. I always thought about that kind of like as a wafer. It is we're pressing that together with a diaphragm on both sides. Okay. I have a process digital multimeter. I have just a HART modem here that we're going to use to interface with our differential pressure device. I've got some regular test leads, and then my old faithful calculator that I got out here. I got to have that. So let's look at the scenario we got. So let's say I have a tank application, and that tank application, let's say, how's my drawing today? Oh, it's looking pretty good so far. So let's say we've got a tank application, and that tank, for us to measure level, our LIT, let's say that tank application has a vent on the top of it. Now that vent on the top is open to atmosphere. So this is a non-pressurized vessel. And let's say we come down here to the bottom, we got a dome roof, and then we've got a dish bottom here. That's terrible drawing, Miles. Let's clean that up a little bit. Let's say we got a dish bottom, a dish top. Let's say we've got our pressure transmitter is actually mounted below high pressure tap point. So let's say it comes down here. There's my differential pressure device right there. And I have a high side, I have a low side. So what we're going to do when we go out there and we put it onto the vessel is I'm going to vent this side to atmosphere. Okay, same as we had here. I've got that vented to atmosphere at the top. I've got the bottom vented to atmosphere as well. Okay, so we're using a differential pressure transmitter. Typically, when you're talking about calculating pressure for a level application with a pressure transmitter or a differential, that baseline equation's kind of been pressure is equal to height times specific gravity times gravity. Okay, is in this scenario we're kind of getting rid of the gravity because I've got gravity being applied here, I've got gravity being applied here, so I can get rid of this and I can get rid of this. Okay, so now we're stuck with pressure is equal to height times specific gravity. So let's knock out what's in the vessel next. Let's pull up some blue stuff. Let's put some fluid in here, and let's say it has a density value of let's say 59.42 pounds per cubic foot. Okay, now for us to get it into a specific gravity unit like my equation is asking for up here, is I got to know what does water weigh in the same units of measure. Okay, so I know this is a density because it's a weight per unit volume, and in this case it's a cubic foot. Okay, it's a cubic foot, so it's a pounds per cubed foot. Okay, now water weighs 62, so let's pull down here. So we got 59, I got my fluid has a weight of 59.42 pounds per cubic foot, and water weighs, if you don't know this, Google it, 62.428 pounds per cubic foot. I divide the two. So I'll pull out my handy dandy calculator, and I say 59.42. I divide that by 62.42. I get a specific gravity of 0.95 specific gravity. So we can just cross this out and replace that with a 0.95. Okay? So now we go back and we look at our equation again as pressure is equal to height, which is still a question mark, times specific gravity of a 0.95. Okay, that's specific gravity is nothing more than that ratio to water. So now we're going to say our height. So almost every device you're going to work on is going to have, what is my LRV, what is my URV, or it might be stated as what is my 4 milliamps, what is my 20 milliamps, what is my 0, what is my 100. Every one of these manufacturers, they're going to call it different stuff. I don't think it's to confuse you, but it's everybody has kind of their own language manufacturer to manufacturer. You as a technician, especially you go across your plant and you're working on 100 different manufacturers of equipment out there, makes you a better technician because you know how they're looking at it. What we'd love for everybody to get on the same page, call things the same thing. I don't think it's going to happen in my lifetime, but we want to understand what that manufacturer is asking for. So we need to figure out what is my LRV and what is my URV, okay? So how much pressure is going to be exerted on the cell at this point right here? How much pressure is going to be exerted on the cell? So let's throw us some numbers in here. Let's say we got 18 inches right here, and that's center line of this crossover to the center line on this crossover. There's 18 inches between those 2 points, okay? So it's this to this. Let's come up here and let's go. My 0% mark, we're going to make it right here at that tangent line. It's kind of the lowest point within this system we can measure because of where we're tapped in. We're tapped in a tangent. I can't tell you what liquid is over here because I'm feeling that pressure above me, okay? Now my 100% mark, let's say we put it right here, okay? And the distance between 0 and 100%, let's just keep it simple. Let's say 120 inches. That's from center to center here. So I have my heights, I have my weights. Now we should be able to calculate our pressures for our LRV, calculate our pressures for our URV. So let's start with our LRV. How much pressure is going to be exerted right there? So we back to that question. So if I take it and I empty this vessel out to this point, how much pressure is going to be exerted on this cell? So it has a height of, pressure is equal to a height of 18 inches times a specific gravity of a 0.95. So 18 inches times specific gravity of a 0.95, that gives me a height of, or a pressure of 17.1 inches of H2O. That's how much pressure is going to be exerted on that cell when the tank is completely empty. So that gives me my LRV value, okay? Let's go up and do our URV. So our URV is everything above this point. It's the same place we're feeling pressure, but now of it just being filled to this point, it's filled all the way up to right here. So I have 18 inches plus 120 inches. That gives me a height of 138 inches. So pressure is equal to height of 138 inches, multiply that times specific gravity of a 0.95, 131 inches. So pressure is equal to 131.1 inches of H2O. We've converted that into pressure now, okay? So LRV is 17.1 and my URV is 131.1. Okay, might want to remember that. I'm going to take a quick picture of that just so I can reference back to it. 17.1, I'm gonna kind of highlight those. 17.1 inches of H2O, LRV. And then pressure is equal to 131.1 inches of H2O. So that's my 2 points. Let's catch a quick snapshot of that, because that's what we got to have to be able to go in here and program into this transmitter that we've got sitting on a bench. We want to be able to take it out to the field with it already pre-configured, stick it onto the tank, and it should work. If we've done a good job making good measurements in the field, we've done our calculations correctly, there should be no reason this should not go into the field almost seamlessly, okay? So let's talk about how we configure this device, okay? I'm saying configuration, I'm not saying calibration. We're configuring this field device, okay? So first thing we got to do is we need a loop. So I'm going to use my process digital multimeter here. And this is one of them features I don't use very often. If I'm out in the field and I'm working on stuff or I'm troubleshooting something, I'm not pulling this meter out and getting it into a loop power mode. It's an oddity. Now, what it's great for is being on a bench and getting a power supply, powering up a transmitter out in the field when you don't have power out there to maybe do a pre-configuration and maybe a new commissioning project. Great for those types of things, but it's not something I use to do any troubleshooting, do any diagnostics on any types of devices. So it's kind of oddity. I don't use it very often. So I'm gonna turn this around where we can kind of look at the back here. And let's see what we got on this side. So I've got a plus and a minus here on the transmitter. So what do we want to do is, this is polarity sensitive. So we need to make sure we've got our positive going to the right place and our negative going to the right place. So I'm going to go off my 7/8 or my process digital multimeter. I'm negative here. I'm positive, see the source plus minus. I'm positive here. And then I'm going to come over to my field device and we're going to land negative, positive. So this should complete the loop. I got positive 24 volts going out on red, coming to here. Okay, coming to here. Then this is regulating the amount of current that we've got going through the loop. It's coming back on the black wire to our negative side. Okay, positive, negative. So all this does is this creates the loop. Turn that around, you kind of should be seeing that power up. It has a boot sequence. Almost every manufacturer has a boot sequence. You know, so when it first powers up, this one goes a little bit above mid-scale. So what's it reading on the display? Not that I really care. We're seeing it go through a boot sequence, and it's going to its home screen now. It's reading 0, okay? So now we have this powered up. What we want to do next is we're going to clip onto this signal. We're going to clip onto it with a HART modem. I can't stand a tangled up cable. Oh, drives me insane. So what we're going to do is we're going to go over here and we're going to be using that HART modem, okay? Nothing special about it. It's traditional HART modem. There's a tons of manufacturers out there that manufacture these things. Find what works good for you and your team again. So we're going to clip across. We're going to clip across it, okay? And this is not polarity sensitive. Not polarity sensitive. We're in parallel. Where we've got the digital multimeter, it's in series with this. Our HART modem is in parallel with this, okay? Now, the one thing that you kind of got to remember is typically when you're going to be out in the field and you're working with, you know, you got a PLC or a DCS system, is most of the time those PLCs and those DCS systems already have the load resistance in it. Now, us being on this bench, another great feature that you see with a lot of these process digital multimeters is you have the ability to drop in 250 ohms of load resistance within this loop, okay? So we're coming across it, we're parallel to it, we need to be able to make a connection. So what I'm gonna do is I'm gonna just come over here and I'm gonna turn on that HART modem, and it's Bluetooth from here to my tablet, okay? So I'm going to make a connection to this device. I'm going to turn this back around where you can kind of see what's going on over there as we're putting it through a boot sequence. And I'm using this, pretty much it's a device descriptor style device. It's simple. It goes in. It's a lot of times. Sometimes you can't do really advanced diagnostics, but this is a great device for like configuration. Been working with handhelds for almost my whole career, you know, and dealing with the different handhelds. You know, some of them are really great, but I think these high-end handhelds, they seem like they're phasing out of the market. And kind of my opinion is it's all about what does your facility need? What do you like as a technician? I saw an acronym the other day is bring your own device, okay? Is nowadays you have interfaces that can use cell phones, laptops, tablets, handhelds. You know, there's a lot of different methods. Used to, we were put in a box. We had to use a certain handheld to be able to commission these devices. Nowadays, it's pretty much open. Things to think about is, you know, what's my area classification? You need to make sure you have a device that is rated for your areas. So that's a major, and it needs to be approved. And the other thing is think about your whole team. Don't think about just you. I went into a facility the other day, and honestly, they had 5 different ways of making connections. The level of confusion within that shop on how to make connections to devices was very discouraging to me. And I got to looking at a lot of them. A lot of them are almost the same thing. And to me, that's just a layer of confusion that probably could be avoided if we took a minute to dig a little bit deeper. But here, we've made a connection to this device. So I made a connection to this device. So what we're going to do now is, let's keep it really, really simple. Is what I see when I made that first connection is I'm getting all my HART variables. My PV, SV, TV, and typically I see that as a QV, but they got it listed as a 4V. But these are HART variables. These HART variables can be changed. You know, most manufacturers can. You can go in there and program whatever you want to be. Not a huge deal in this scenario, but if you had one that was a multi-variable device that we were trying to pull multiple parameters off of, we could pull that via HART, okay? So the first thing I do is, you know, without going very deep, is what are we using this one for? Is it a pressure? What type of device is it? Now, we're going to keep it simple. We're just going to say we're going to measure it as a raw pressure. Even though we're going to convert it into a level measurement, we're going to keep it simple. We're going to keep it pressure because the way we did our calculations was via pressure, okay? So let's go through and let's do a quick setup. So in the device info, you can go in there and you can put tag, long, description, messages. You know, you can go in there and program that short tag and that long tag and maybe even the description of where this device is within the network. You know, a lot of times that's great, has value. Units of measure, we got to program those. Now, when we went through and we did our configuration, we configured ours for a pressure units of inch of water column. And it looks like this is the way this one was set up kind of default. But you can kind of see there are a lot of different units out there that are possible from PSI to, you know, but think about it. This is a raw pressure measurement. You're not going to find that percent of level. You're not going to see gallons a minute if you were doing a differential pressure for a flow. These are the raw pressure measurement units, okay? So in this case, we're going to stick with this inches of water column. Degrees F, that temperature is how hot is the sensor itself, okay? So it's not one that we're using to program or to do any kind of calculations. It's looking at how hot the temperature is getting. So then we're going to go in here and we're going to set our LRV and our URV. Now that might say set 4 milliamps, set 20 milliamps. It might say set 0%, set 100%. So we need to find our picture here. And what we needed my pressure at 0%. My LRV value, my 4 milliamps is going to be 17.1 inches of water column. I'm going to hit that. And then this is like the send. It's a commit. It's taking that information and pushing it to the transmitter, okay? Before I hit commit, it's only at this point. When I hit commit, it pushes that signal this way, okay? So that sets my LRV value. Let's go in and let's set our URV. So what do we have in for our URV? Let's look. We had 131.1. 131.1 inches of water column. Got it here, still just sitting here. We're going to push that to the transmitter, okay? So now I have this device programmed to what I had in this scenario, okay? It's exactly what we had here. Now we've actually have it here, okay? Now the last thing I try to tell people is that there's a lot of things you can do, advantage, but one thing that I try to do is once I get this thing put into place, is you have this thing, it's called position zero adjust. Okay, it's a lot about how is this device orientated? Is it on its side? Is it sitting upright? How is it sitting? And then before I put any fluid on them, I'm going to do a position zero adjust. And all it's doing is it's saying the pressure that I feel here versus the pressure I feel here is we're going to make it zero. Okay, it's zero in that device, high side to low side. Okay, so right now we're seeing, 0 inches of water column pressure being showed here. We're probably going to get some kind of fault. Let's see if we get a fault here. Maybe not a fault, but more of a warning. Yeah, it does. It says current out of range. Okay, now why would that be? It's because we told it when we were looking at this configuration, is we told it that it would always have this pressure right here. But right now, sitting on the bench, it doesn't have that pressure. It doesn't have that elevated zero, okay? So it should be in a fault. It should be in a warning that says, hey, I don't feel my LRV value, okay? Now, when you first put it in, you're going to see that. But once it gets that leg filled, and that leg is filled, and it's maintaining that reference point for our measurement, this thing's going to rock. It's going to rock. So we have the configuration done. Now we could actually take it out there, put it in the field. It's ready to go. That's one from a configuration point of view, us doing the calculations and then applying those to the configuration of the device. There's not a lot here. I tell people this all the time is, I see technicians today, we can hand them a data sheet. They can take that data sheet and they can take this handheld device and they can go out there and they can take the information that's on the data sheet and they put it in the transmitter. Great, works great, okay? That's not the hard part. It's understanding where the information is coming from, because where it's gonna get to at some point is they're gonna go, this ain't working. This is not doing what it's supposed to be doing. It's not reading the right level. Well, what are we gonna do? Well, all we know how to do is go out there and take that data sheet and make sure it's the right number. The numbers don't change very often here. Once you program, it's very rare I see a transmitter, that does not hold those values. Something has changed. If you don't understand where the numbers are coming from, how are you ever going to be able to troubleshoot this device? Okay, so keep that in mind. This is taking one from very, very beginning to very, very end. Last thing I want you to think about before I jump off, we'll put some information in the comment section, but why are we reading 3.8 milliamps right now? Okay, why are we reading 3.8 milliamps? That's a question for you to take back and think about, because we've talked about it already in the basic setup program. Is think about why that 3.8's there. Think about what's happening right now and why we're seeing that. So I hope this little practical helped you out a little bit. Lots more of these to come.